multi-mode modulation, PCM, it's a codec. It's a way to convert our analog data to digital data. Our continuously varying audio, for example, into bits. And what we do is we take samples at regular intervals in time, and each sample we measure the magnitude of the input and map it to a code number, which is this block of the quantizer. So we have our input, we sample every TS seconds, so some sample period, and obtain some value, and then we map that value into the nearest code number, or sometimes we've said the nearest level, to get discrete values. And then simply that code number is converted to an n bits of data, called the PCM code in this case. So the concept, sample, map to one of the code numbers or levels, and then you can get directly the data as the output. The things of interest, or the parameters that we have here, are how many samples per second do we make, the sampling rate, and how many code numbers do we use, or how many levels do we use. And we finished yesterday saying that the trade-offs we have, if we increase the sampling rate and we increase the number of code levels, our quality will go up. If we sample more and we have more code levels, the quality of the reproduction of that audio, or not of the audio, of the analog data, doesn't have to be audio, the quality will go up. That's a good thing. But if we increase the samples per second and the code numbers, the number of bits that we need to store or to represent that analog data goes up as well. And we saw an example where we had 3 cases yesterday where we varied the sampling period, or decreasing the sampling period increases the sampling rate, and we varied the number of levels or code numbers. And we saw the impact that it had on the data rate required. Although I went through quickly, with CD audio, if you sample at 44,100 hertz, you can fit about 70 minutes or 66 minutes on a CD. If you doubled the sampling rate to record audio, you would only be able to fit half as much music on the CD. Because if you double the sampling rate, you'd have twice as many bits to store on the CD. So increasing the sampling rate can increase the quality, but increases the amount of data we need to represent that analog input. Okay? So that's the trade-off we need to consider. And what we want to get to today is, well, what is a good value for the sampling rate? And I've just given a hint in the example. Nyquist did some work, the same guy who talked about the capacity, and they come up with the sampling theorem, which says if the input analog data or signal, remember it's some continuously varying data or signal that has some frequency components. So the input f of t, if it's sampled at regular intervals, that's what we do with PCM, sample at regular intervals, at a rate that is higher than twice the highest signal frequency, then the samples contain all the information of the original signal. What that means is if the input, if our analog input let's say some function of time, so we have some equation to represent the input, some sine values or whatever, but if the highest frequency component remember our signal or data is made up of multiple components and they have different frequencies, and that gives us the spectrum of that signal, and there's the highest value and the lowest value. The difference gives us the bandwidth. Considering the highest frequency component of that input, if we sample at a rate, if the highest frequency component, say, let's call it, did I use it? simply f here. If f is the highest frequency component, if we sample at a rate greater than or equal to 2 times that, f, then that's sufficient for the sampling rate. When we do that sampling, we'll be able to reconstruct the original analog input, recovering all the information from the analog input from that data. So if we know the structure of the analog input, and in particular we know the highest frequency component, say f, and we sample at 2f, then we'll be able to reconstruct that analog input. This is ignoring something about the code numbers at the moment. We'll have to come to that in a moment. But that's what the sampling theorem says. So if you sample at less than 2f, you'll know that you'll get lower quality because you'll have a lower sampling rate, and you will not be able to reconstruct the entire analog input. We're not going to explain and go through the maths of why that is. Similar when we looked at the Nyquist and the Shannon capacity, we just gave you the formulas. Here we need to remember the sampling theorem. Sample at twice the highest frequency component to give the optimal quality in the reproduction. If you sample less, you will not get the optimal quality. If you sample at 3 times f, 4 times f, it will be the same as sampling at 2 times f. There's no need to sample any higher. What's an example of that? Audio, the example with CDs. One of our earlier slides, maybe in one of our first lectures, we had some plots that showed the spectrum of voice. When people talk, their voice ranges in several hundred hertz up to several thousand hertz, whereas music ranges from several hundred hertz up to maybe 10, 20,000 hertz. So when people create music and so on, let's say the highest frequency component is 20,000 hertz, therefore the optimal sampling rate is twice that, 40,000 hertz. And that's why when they record audio CDs, not MP3 CDs, but audio CDs, they use a sampling rate of 44,100 hertz. It's twice of the highest frequency component they expect to have in the audio music. If your voice contains the highest frequency component of 4,000 hertz, then you should sample at 8,000 hertz. That is 8,000 times per second. So that's what this sampling theorem tells us. Of course, we may not be able to sample at that rate. That is, we may want to sample at a lower rate, but that means we'll get a lower quality. So if we sample at less than 2 times f, we'll get a lower quality. If we sample at higher than 2 times f, we will not improve the quality because this is sufficient. We cannot get any better. So it gives us the best value. And the example here, voice typically considered between 0 and 4,000 hertz when you talk. Therefore, according to the sampling theorem, we should sample at 8,000 hertz or 8,000 samples per second. And that tells us if we do that, then we'll be able to reproduce the analog voice at the receiver. In theory. In practice, there's another factor that limits the quality, and that's the number of code numbers or levels. So there's 2 things that impact on the quality. The sampling rate, and we have a theorem that tells us what the ideal sampling rate is, but there's another factor, the number of code numbers. If we had an infinite number of levels, then we'd be able to perfectly reproduce the analog input if we apply the sampling theorem. But in fact, we don't have an infinite number of levels, we have a discrete a finite number. So it depends upon what the audio input is as to what the good number of levels is. It turns out with voice, people have done tests and found out that using 7-bit coding, that is 128 levels or 128 code numbers with voice, is usually sufficient to give good quality voice reproduction. That is, if you play back some voice recorded with a sampling rate of 8,000 hertz and 128 levels, then what your ears will hear will be almost a perfect reproduction or a sufficient reproduction of what the original voice was. With music, it's different. As we've seen in this example, music has higher frequency components, therefore we need a higher sampling rate. And we need more bits normally to reproduce it, because we normally want music to be a higher quality than voice. So we use more bits, say 32,000 levels in this case. So it depends upon what the analog input is as to what is the optimal number of levels. So when a codec is chosen, then you need to make that trade-off, the sampling rate and the number of levels. Increasing them, better quality, but more data needs to be stored to represent that analog input. That is, either a higher data rate to transmit it, or more bits are needed to store it, if you're talking about storage on a hard drive or some medium. If you look at, and there are many different codecs, PCM is the main one we've looked at, but there's no compression in there. MP3, FLAC, all the other audio codecs that you use to play audio on a computer, they are codecs. So they have their own algorithm for how to encode the input data, the analog input, and save it as digital data. But many of them also apply compression as well. So they apply some other algorithms to, instead of having to store all of the bits, they can store some smaller representations of those bits to save the space in which they store that same data. We will not cover compression in this course. But they are examples of codecs. Any questions on PCM? I think that brings us to the end of this converting analog data into digital data. We've covered just PCM. There are others as well. The remaining slides here just give a few more examples of some extensions of PCM for different cases. We're not going to go through these, how they work. Some ways to improve how PCM works. And an alternative, delta modulation. You can see, and you'll see in some past exams that I've given this as a question about delta modulation, but we haven't covered it in the course. Yeah, you can look at that in your own time. Last approach. How do we transmit our analog data using analog signals? Come back to our audio system. I'm talking, that's our analog data as an input. And the audio, the microphone picks that up and sends some electrical signal to the wireless transmitter, which actually sends analog signals to the receiver, which also sends analog through to the amplifier. It's an analog amplifier, and up to the speakers and analog to your ears. So that's an example of the original. We can think of the analog data as input, transmitted as analog signals. In that example, the analog data on input ranges in frequency, so my voice ranges in frequencies up to several thousand hertz. So let's say 0 up to 4,000 hertz to keep it simple. One thing we can do to transmit analog data as analog signals is to simply carry them as is. Do not modify them, because the input is some analog signal, effectively. The data is some varying waveform, and we just transmit that as across our transmission medium. And that's what a telephone line does. A home telephone line. The phone just takes the audio signals and converts it to an electrical signal to send across the cable within the same frequency range. So imagine the audio input is some sine wave or some waveform. What your telephone does, your home landline telephone, is takes that, because it's audio, it converts it to an electrical signal that's sent across the telephone line, and it's the same shaped waveform sent across the telephone line and covering the same frequencies. So that's an example of an analog input sent as an analog signal. There's not much to do there, just convert the audio to an electrical signal. But sometimes we want to change the frequency or the spectrum of the signal that's transmitted. In the example of the telephone, the input has a spectrum ranging from 0 up to 4,000 hertz, and so does the signal that we send. But in some transmission systems, we'd like to change and use a different range of frequencies for the signal, because we know that sending signals at different frequencies has different characteristics. It can cover different distances, propagate through obstacles in different manners. Sending signals at different portions of the spectrum have different advantages and disadvantages. So one form of, or the main issue of sending analog data as analog signals is really shifting the frequency of the signal compared to the analog input. What we do is we have some input signal, and we use what's called some carrier. We carry that input signal on some other signal and produce some signal that we transmit S of t. So, as a different example, here's our input, let's say M of t. And if we want to transmit that across our transmission system, not using the spectrum 0 to 4,000 hertz, but at a different frequency, let's say we want to send it across the air from a radio station to your car using AM transmission, so AM radio. Then what we do, and with AM radio, what's a typical frequency of AM or even FM radio? FM 105 what? 105.5 megahertz. So let's say FM radio 105 megahertz. So that means the signal is transmitted at a frequency centered around 105 megahertz. In fact, it's centered around that. The signal, because it has a range of frequency components, is plus or minus a few, probably about 20 kilohertz. So this is the signal that we need to send with FM radio. This is the input, someone talking. So we need to shift this from the 0 to 4,000 hertz up to a frequency of around 105 megahertz. And what we do with FM radio is we apply modulation. We vary some carrier signal. So we have a carrier signal which is at 105 megahertz, a frequency of 105 megahertz, so just some sine wave at 105 megahertz. And we modify that carrier signal based upon the input data. In particular, we modify the frequency of this slightly when the input, let's say when the input data is high, we use a higher frequency. When it's low, we use a lower frequency. So this carrier signal actually centered around 105 megahertz, but varies slightly. And that's the signal that we transmit. We modulate the data onto the carrier signal, varying the frequency of the carrier signal. Hence we get frequency modulation, FM. And we can change either the frequency to get frequency modulation, the amplitude modulation, or the phase modulation. Let's show them, or examples. Here's an example of amplitude modulation. This is the input data, a simple sinusoid as an input data. That's what we want to send. You see it has a low frequency. We have a carrier signal with a high frequency, okay? And the output signal, the signal we actually send, we take the carrier signal, and with amplitude modulation, we change the amplitude of the carrier signal depending upon the input data. So in this case, we see that the pattern of the amplitude of the carrier is following the input data. When we've got a negative value here, the amplitude is low. When we've got the high peak value here, the amplitude is high. So this is the signal that's transmitted. It's based upon some carrier signal of some frequency, and the amplitude changes depending upon the input. So the input and the transmitted signal. That's our amplitude modulation, AM. That's what AM radio does. It takes the input music or people talking, and with AM radio, let's say you're using a frequency of, what are the frequencies? Lower. What's an example AM radio channel? 900, usually range, what is it, 900 kilohertz, is it? So there's different frequencies for AM radio. So that would be the frequency of this carrier signal. So that'd be varying at 900 kilohertz. And the amplitude of that signal would change depending upon the input data, what people are saying or the music that's being played. Same with FM modulation. All right, this also shows amplitude modulation. Here's the carrier at some frequency. Here's the input data, the simple example of the input data. And this is the output signal that's transmitted. The carrier is modulated by the data. And the others are similar, except instead of changing the amplitude of the carrier, we change either the phase or the frequency. Here's our carrier with phase modulation. Again, our input data, we change the phase of the carrier depending upon the input here. It's harder to see exactly why it would look like this, but if you do the mathematics, you'll get this shape signal. And similar with frequency modulation, FM radio, for example. We have some carrier signal, let's say at 105 megahertz. That's the frequency of the carrier. We have someone talking or some music being played. That's the input, this modulating sine wave signal here, the second one. And as that varies, the frequency of our carrier varies. So although it's centered around 105 megahertz, it changes plus or minus some values. You see, it's a lower frequency here, it's a higher frequency here. So maybe this is 104.9 megahertz, this is 105.1 megahertz. So it varies slightly around that center carrier frequency. And the receiver receives that and measures the variations, that is, measures the difference between the expected carrier and the actual frequency, and determines what the input was and plays that back. So that's how we often send analog data as analog signals. And in all of these cases, we can transmit our data no matter what the spectrum of the input data is, voice of just 0 to 4,000 hertz, we can transmit it at any frequency in our spectrum. FM radio, the voice, is transmitted at, say, 100 megahertz approximately. When my voice is input into the microphone and goes to the wireless transmitter, this transmitter from memory transmits, I don't think it says here, actually I can't remember, I did it last year, some wireless transmission of, I think it was, what was it, 700 or 800 megahertz is the frequency of the wireless transmission from this transmitter to the receiver on the desk. So the voice is transmitted using, what was it using then? I think it was using FM in that case, frequency modulation, to transmit that voice from the wireless transmitter to the receiver at a much higher frequency. And then it's converted back down to the original frequency when it's passed up until the speakers and then down to your ears. So AM, PM, in terms of amplitude modulation, phase modulation, and frequency modulation, FM. Are the three approaches we have for analog data as analog signals. Quick through them, because that's all we need to say. Just understand that we vary some carrier signal, we vary its amplitude, frequency, or phase, depending upon the input data. Any questions on those three?
We do that to avoid using that particular list.
So one of the advantages we have here is that we can now shift our input data to any frequency that we choose. So another case, so we can use different frequencies, and for example we can have different channels. We have 105.5 for one radio transmission and some other 106.1 for another radio transmission at the same time. So the transmitters can transmit at the same time, but they're both transmitting voice, which ranges from 0 to 4,000 hertz, or even music. If we transmitted at the original input signal, they would interfere with each other. But by shifting them to different frequencies, they do not interfere with each other. So the advantage is that we can transmit at different frequencies than what the original input is. Allows us to transmit things at the same time at different frequencies. Any other questions on any of those topics of how do we send our data as signals? Because that brings us to the end of this topic. Phase and frequency modulation effectively the same. You look at the output. Because if you change the phase of that sine wave, maybe the best thing to do is to try it yourself and plot it. If you change the phase, you are effectively changing the frequency or equivalent to changing the frequency when you're doing the modulation. So that's why they look the same here. Of course, in different ways, but here we have a lower frequency, high frequency, and a low frequency just by changing the phase. Hence, phase modulation is not so common. You have AM and FM because you can effectively do the same of using FM as phase modulation. And in theory, you've got all three options.
Does the frequency of carrier always be 105?
The frequency of the carrier is what your transmission system is designed to use. For example, with FM radio, one company gets a license to use frequency 105.5 as megahertz as their carrier signal. Okay, and the way that those licenses are allocated, another company can get a license at a different frequency, and they need to be separated by enough such that they don't interfere with each other. Because remember, we don't transmit at that exact frequency, we transmit at a range of frequencies centered on 105.5. Our signal that we send has a range of frequency components. And similar, this signal has a range of frequency components, centered about 106.1 megahertz. The center frequency is 105.5, but there are components on either side. And the channels are assigned, or the licenses to use the channels are assigned such that if you use this center frequency, you cannot transmit at a wider bandwidth than this, so that you will not interfere with someone using a different channel. So the carrier frequency can be any frequency. In practice, say with FM radio, it's based on the licensing, so that the different FM radio channels can be all transmitted at the same time. They do not interfere with each other. All you do is change the tuner on your receiver to tune into the right frequency.
Who issues the carrier frequencies?
Sorry?
Who issues the carrier frequencies?
Who issues the carrier frequencies? Usually governments, some licensing organisations. So, for example, in Thailand, I don't know if they do radio, but at least now MBTC, they do TV, and so the National Broadcasting and Telecoms Commission allocate licenses for TV, also for mobile phones. Same concept. With a mobile phone system, you have frequencies allocated for your transmissions. And they're allocated such that if you use it and someone else uses another frequency, they will not interfere. And because they're limited, there's only a certain range of frequencies reserved for mobile phones and another set reserved for FM radio and another for TV. They're limited, therefore there's competition to use them, therefore there's a lot of money to pay for the license.
How do they prevent it from going out of
like? So how do they prevent them from interfering? So there are regulations such that what was it? I can't remember the exact bandwidth, but I think a bandwidth of around 20 kilohertz. That is, so from the center frequency, you're allowed to transmit a signal, if you look at it like this, from plus or minus the center frequency such that the bandwidth, the difference between the minimum and the maximum, is 20 kilohertz. That's the bandwidth. And the transmitters must be designed to transmit at a no larger bandwidth. For example, they can use filters to filter out any lower frequencies in the transmitter. So if you transmit at a wider bandwidth, you are breaking the rules, the conditions of your license, and you can lose your license, for example. So there are commercial or financial penalties in that case. Same with your Wi-Fi, wireless LAN. You know, when you connect to a wireless LAN network, normally a channel is assigned. Maybe channel 1, channel 6, channel 11, if you look at the details. Same concept. A channel is just a different center frequency. So I can communicate from my laptop to the access point out there using channel 1, and someone else in the other room can communicate between a laptop and an access point using channel 6. And they're designed such that they will not interfere with each other. They're separated by enough such that our signals will not interfere with each other.
When you're in a certain part of the country, if you turn to a certain frequency, but when you're in a different part of the country, you get the same. You get different channels. Limit the area.
Our signals only propagate some distance. So for example, the transmitter, let's say the FM radio transmitter owned by the radio station, some tower, they transmit the signal. It transmits at some power level, the transmit power. And over distance, the power gets weaker, and your car antenna has some antenna gain, and you can receive some power level and understand it. As you drive further away from that transmitter, the signal will get weaker and eventually be too weak to be able to receive and play back the radio.
So then, do they limit a certain distance?
So yes, so when the organisation allocates licenses across a country, across Thailand for example, there can be licenses to use say 105.5 in Bangkok, and another company can get a licence to use the same frequency in Chiang Mai, because they're so far away that they will not interfere with each other, and similar at different locations. So again, there are limits on the transmit power of the radio stations. So they know approximately the distance at which they'll transmit. Who has chose their options? CS option 1 and 2. What option are you doing?
Not sure.
Not sure? Anyone? So you've got a choice of software engineering and what's the other one? Informatics. Okay. If you do the IT as an elective, we cover wireless transmission more. In one of the IT options, we cover internet technologies and applications covering wireless, Wi-Fi and so on, and you'll learn more about this, okay? But in the case of your CS students, you need to choose it as an elective. Maybe next year you can do it. Let's move on to the next topic. And this topic we're going to skip because we're a bit behind. We're going to skip this. It's only a short topic anyway. We're going to skip this. We're going to say just one slide on what the concept is. Now we're talking about, we're going to move up to the data link layer. Really, most of the things we've talked about are related to the physical layer. How do we send signals? How do we represent data as signals? Now we're going to look at, especially digital data. When we want to send digital data, how do we send it such that it's reliable? Because we know that when I send some signal, the received signal is not going to be exactly the same as what's transmitted, because there's noise, there's interference. And therefore we're going to get errors at the receiver. If there are errors, what do we do about it? And that's really what this topic's about, and even the next topic. This is about some techniques for detecting errors in our digital data, and in some cases correcting errors. And I think we know what an error is. Now if we focus on digital data, if we transmit a sequence of bits, sequence of 8 bits. We transmit a signal representing those bits, and the receiver receives a signal, maps it back into bits, and the receiver gets this. Then we have a bit error at the receiver because we notice that this bit here was transmitted as a 1. The receiver made a mistake. Maybe there was noise in the system such that the receiver thought it was a bit 0. That's a bit error. This topic is about how does the receiver know that in the data that it's received there are errors? How does it detect errors? So error detection. So it's about what are bit errors, how do we detect errors? And you've covered some of the techniques for how to detect errors. There are different ones. You've most likely heard of or covered parity bits, parity checks, maybe in a computer hardware topic, where we add some extra bits when we transmit, some parity bits. So we transmit our data plus some extra information such that the receiver can use that extra information to detect if the received data is correct or not. So error detection is coming up with a decision at the receiver saying, is the data correct or not? If not, we've detected an error. If it's correct, we're okay. Parity checks are one approach. Others you've probably heard of in terms of files, and there's different CRCs. CRC checks. So what is it? A cyclic redundancy check or a cyclic redundancy code. So they're algorithms such that we add extra bits to the transmitted data, and when we transmit, even if there are errors, the receiver can use that extra information to detect if there are any errors in what was transmitted and make a decision, error detected or not. There are different algorithms for doing that. And that's what we were going to cover, but we're not going to cover, how those algorithms work. What do we do if we detect errors? Resend. And that's what the next topic's going to cover and we'll go through in detail. So resend is one approach. I detect an error at the receiver. I tell the transmitter, please send again. We'll cover that in detail. Another way to correct errors is, again, instead of the data, manipulate that data and send some code that represents the data such that the receiver, even though there may be errors in what they receive, they can correct those errors without asking for a resend. So there are approaches such that we want to send this data, we change it into some other sequence. I'm just randomly choosing this sequence here. Some other longer sequence, transmit this, even if there are errors, if we do it in the right way, the receiver may be able to correct those errors. That is, get the original data back. That's error correction, or specifically forward error correction. The receiver can correct errors without asking for a retransmission. Unfortunately, we don't have time to go through and explain how this semester. It's an interesting topic, but just because of time, we're going to go on to the next one. But understand now, when we transmit our bits, we can have bit errors. The receiver has methods for detecting those errors. Not detecting necessarily where the errors are, but just simply knowing in this sequence of 8 bits, there is an error. It may not know that this bit's in error. If it did, it could fix it. But error detection is really about, in the bits that I receive, somewhere there's an error. There are algorithms that do that quite easily. The problem with those algorithms is that we need to send extra bits. By sending extra bits, then we are less efficient. There are also algorithms that can correct those errors. Again, it reduces the efficiency in some cases. Let's look at a different way to detect and correct errors, or correct errors, which is the next topic. Now we're really into the data link layer. Physical layer sends signals across the link representing some data, and we're going to focus on digital data. Data link layer, applying some protocols to do error correction and some other features which we'll see in this topic. We're going to look at the concept of what is a data link control protocol. We'll look at first flow control and then error control. Error control is what we just said. Error control is saying if the receiver detects an error, ask the transmitter to send again, to retransmit. That's one way to control errors, or to correct errors. But first we'll go through flow control. So, physical layer concentrates on how do we send signals across some link, where those signals represent some data. But to establish the link and to reliably transmit the data across the link, we need some other features, and that's where the data link layer protocols come in. We now talk about not just signals and bits, but sequences of bits. For example, we often call it a frame. This sequence of 8 bits, we can call a frame of bits, or a frame. So now we talk about not just a continuous sequence of data, but blocks of data. With digital data, we normally refer to them as a frame. A frame size may vary depending upon the protocols. Here, the frame is 8 bits. In Ethernet, the frame size is 1,500 bytes. Okay? In different protocols, the frame, the block of data that we deal with, differs. But we talk about sending a block or a frame of bits. So we transmit a block at a time. If we do that, one of the problems that we need to deal with is that the receiver knows where one block starts and finishes and where the next block of data starts and finishes. They need to somehow synchronize where the frames start and finish. We need to give addresses to devices. That's something we haven't talked about with a physical layer, but we know in order to deliver the data to the correct destination, we normally need to specify the address. If we have a set of devices using wireless transmission, A, B, C, and D, and they transmit such that when one of them transmits a signal, it goes in all directions. It's an omnidirectional antenna. And it goes other directions as well. Like your laptop, when it transmits, the signal goes in all directions. So if it transmits a frame, a sequence of bits, some data that it wants to send, we need to specify who is the destination. Because in this case, if A transmits a signal, everyone around it will receive that signal. B, C, and D will receive it. So as well as sending the frame containing the data, we'll also need some addressing scheme. For example, as well as the data, we'll say that the destination address is computer D. So that even though B and C receive that data, they know it's not to them, it's to someone else, and they'll ignore that data. So we need addresses to identify who is this data going to. And similar, when you receive data, you often want to send back a response. So you need to know who sent it to me. So you need to know the source address, who sent it and who received it. So in the data link layer, we normally introduce addressing, that is, how to send addresses with the data and what are the structure of the addresses. We've seen examples with your LAN card, your wireless LAN, you get this 48-bit address, which is these 12 hexadecimal digits. That's an example of a data link layer address. So we need addressing. When we establish a link, in some cases, you connect from your home ADSL modem. Who's got a home ADSL modem? Anyone? No? Who's seen one? Okay, with a home ADSL modem, then it plugs into the telephone line, which eventually goes to a telephone exchange. When you turn it on, there are some lights that flash, because what happens before you can send data is that it establishes some connection to the other endpoint. It sets up some connection to get prepared to send the data. So there's some process of managing the link, setting up and maintaining that link from one endpoint to another. There are different protocols and different ways to do that. So those are some of the features that are needed for the data link layer control protocols. And the two that we're going to go through are these two, flow control and error control. Error control is easy to understand the concept. When we send our data, if there are bit errors, we need to fix them. We need to correct those errors. And the basic approach we use is send the data. If the receiver detects errors, it will ask the source to resend the data, retransmit. That's error control. Flow control is to make sure the sender doesn't send too fast for the receiver. It doesn't overflow the receiver. We'll explain that in some more detail. Before we go into them, we'll explain some basic concepts in the diagrams. So for now, what we're going to assume is, from now on, digital data, the data we're sending is bits. If we talk about audio, then we talk about converting that audio to bits, to digital data. We send our data in blocks called frames. So we send a block of bits. one block at a time. And we'll normally attach a header to that block of bits, including some addressing in that header. So we'll see some example structures there. Let's start with flow control and just explain the concept. What happens when I talk too fast and you can't understand what I'm saying?
Yeah.
What happened then? If I talk too fast and you cannot take in what I'm saying, then what happens? Then you do not receive everything that I'm saying, and that's a problem. We do not communicate correctly. If someone talks too fast and you cannot take in all the information that they're communicating, then you lose some of that information. If someone talks too fast, then they overflow the receiver. How do we stop that? If someone is talking too fast and you cannot take everything in, maybe I'm going through the lecture too fast, what do? Tell them to slow down. Okay, that's flow control. When we have a computer that sends our data too fast, such that the receiver cannot receive it and process it, then somehow the receiver needs to tell the sender, slow down. And that's what our flow control protocols do. And why would someone send too fast, or what's the impact of a transmitter sending data too fast? It comes down to where is the data stored at the receiver. This diagram tries to show it from a layered perspective. At the bottom is the physical layer. Here are the two devices, one computer and another. This is the transmitter and this is our receiver. This is the data link layer, and above it we have the network layer, and above we ignore the details. What happens when we want to send data from A to B? What happens is that we have some data to send, and the network layer inside the computer stores it in some memory, some RAM inside the computer. And when the data link layer is ready to send it, it creates a frame, some sequence of bits. It adds some header, including some addresses, and transmits that frame, so it processes the frame and transmits the frame across the link. And of course we may have a lot of data to send. We have a 1 megabyte file to send. Every frame contains, say, 1,000 bits. Then what happens? We send that 1 megabyte file, store it in memory here, and the transmitter takes one frame, transmits the next one, then the next one, and so on. That's the role of the transmitter. What the receiver does, as it receives frames, it stores them in memory at the receiver, and then processes them and takes the data and sends it up to the network layer. This memory size is limited. It's RAM or some memory allocated for the receiver. The problem arises if, for example, the memory is a size such that it can store 10 frames. If the transmitter is sending too fast because this is slow at processing the frames, it's got a slow CPU, then once 10 frames arrive and it's still processing it's still processing a frame. If there are 10 frames that have arrived, then they're stored in memory, and there's no more space in memory. So if an 11th frame is transmitted and arrives, what happens? Where does the 11th frame go? So my receiver has space in memory for 10 frames. It's currently storing 10 frames in memory. An 11th frame arrives along the link into your computer. Where does that frame go? It disappears. It doesn't go anywhere. It is discarded, we say, or lost. That is, we cannot store it in memory because the memory is full. So the receiver effectively receives a frame and throws it away, discards that frame. It's lost. So we lose some data. That's a problem. Or another approach it could do is throw away the data in memory and store it in memory. But the point is that we're going to lose data if we have a limited amount of memory here and the transmitter is sending too fast such that it fills up that memory. Then we're going to lose data. And that's a problem. We don't want to lose data like that. And what are we going to do? What will the receiver do? What's the receiver going to do? If the memory is full, what do you think the receiver will do? It will discard, but how are we going to avoid discarding data? We don't want to lose data. How do we stop it from happening? I don't want to lose data, so how do we stop that from happening? Again? No, we cannot compress. Request for resend, again, that's not good. If we lose it and need to resend, that's inefficient, we'll see.
Allow the CPU to process the data first.
But my CPU is a fixed speed. I cannot speed it up. It's processing as fast as possible at the receiver. I have a fixed amount of memory. It's full. I can't process any faster. What do I do? Control the speed, so somehow the receiver needs to control how fast the transmitter is sending. And so that it says, okay, the receiver recognizes my buffer is full, my memory is full. I cannot receive anymore. So what it can do is send a special message to the transmitter saying, my memory is full, please do not send me anymore. And until it has some space in memory, and it may send back another message saying, okay, I now have some more space to receive more, you can send more. And they keep doing that. And that's how the receiver controls the flow of data that it receives. It tells the transmitter to slow down or to speed up if needed. So that's what flow control is. The receiver controlling the rate at which the transmitter sends the data such that the buffer at the receiver is not filled up. The memory is not overflowed. We'll go through specifics of how we can achieve that, specific protocols. We'll go through them next week. So with the data link layer, we're going to go through flow control and error control. Next week we'll go through how the flow control works, some specific protocols. For the last 10 minutes today, we can, I think, talk a little bit about the assignment and the midterm. But before we do that, any questions on anything we covered today? PCM, the modulation techniques, or the concept, just the concept of flow control? It's a simple concept. There are different ways to implement that concept. The receiver will control the speed at which the transmitter sends the frames. The link speed is fixed, for example. The link speed may be 1 megabit per second. Every time we transmit a frame, it's going to be transmitted at 1 megabit per second. But the transmitter doesn't always have to send frames. So what the receiver will say is, please stop sending frames. And therefore nothing will be sent for some period of time until it has space in memory.